The Physics 2212 Lab 5 Faraday's Law. A quick introduction to the lab. The purpose was to collect data on the time it took for a bar magnet to fall through a non-magnetic, we used an aluminum, tube, and a computational model to understand Faraday's law in the real world. The key concepts for this lab are Faraday's law, the Biot-Savart law, and Newton's laws. Faraday's law is the relation between induced voltage and the changing magnetic flux through a certain area. The Biot-Savart law is the magnetic field created by a moving charge, and Newton's laws come into how the magnetic field slows down the falling magnet. And a quick preview of the results, we measured the time to fall through at an average of 0.69 seconds. The modeled time using a dipole moment from lab 3 was 2.979 seconds, and when we adjusted that mu value, we got it to the computation model to put out 0.691 seconds. These were the measurements from the initial experiment. The foil was 30 centimeters in length, 6 millimeters in width, with an inner radius of 24 millimeters and a total radius of 30 millimeters. The magnet was 0.26 kilograms. The dipole moment that we took from lab 3 was 7.55, and the adjusted dipole moment that I was talking about earlier we used as 3.55. These are all our trial times in the average right here. So this is the first part of the glow script model, and all it's doing is outlining your physical constants, starting your graph, and it's creating the aluminum foil object as a stack of rings, essentially. And now these are just like certain numerical parameters and creating all of those rings for the aluminum foil. This code was given to us. Here we put in the measured values of our bar magnet, so its mass and the dipole moment, and then it creates that cylinder object that represents the bar magnet in our experiment and sets its initial velocity at 0. We write a function to calculate the magnetic field of the bar magnet using our mu and a certain distance. So this was taken from lab 3 and an equation we were given for that lab. And then we're using a function to calculate the magnetic flux through the ring by essentially calculating the magnitude of the magnetic field that is in line with the normal vector and multiplying that by the area of our rings based off of the input parameters that we were using to calculate the flux. And then we take the time integral of that formula to get our change in flux over time. This is just a loop that will keep calculating the induced magnetic field from the induced current while the bar magnet is still within our tube. This next step is creating our gravitational force vector, and then it uses this next for loop to create the magnetic force vector. This is the rest of the calculating the magnetic force, and we can see F magnet is just the magnetic force that is on the magnet. So the net force on the magnet is right here, where it's our gravity force plus our magnetic force. And then this is using Newton's second laws just to calculate its acceleration and position from the net force that is acting on it. And then all done. Two velocity versus time graphs that we got out for our different mu values. Here on the left, you can see the velocity versus time graph shows almost a constant velocity for the majority of the bar magnet falling through with the higher mu value. And this just shows that at those points, the magnitude of the magnetic force was equal to the magnitude of the force of gravity acting on it. So it had no change of velocity until it started getting to the end where less loops of the foil were interacting with it. Here you can see a little bit more reasonable graph, which is closer to what was really happening, where there's a very quick acceleration due to gravity. Then as it starts inducing more current and more magnetic field, they cancel out until it's roughly constant, and then it drops out when it stops interacting with the loops. So this is the model of the roll of aluminum foil. The red lines are showing induced current in the clockwise direction when looking from the top. We determine that using our right-hand rule, and the blue lines are counterclockwise when looking from the top, and the relative intensities show the relative strength of the induced current in that ring. What if the resistivity of the conductor were reduced as close as possible to 0? How would the dynamics of the falling magnet change? So if the resistivity dropped, the induced current would be very large, meaning the induced magnetic field would increase in strength, and it would spend more time in that constant velocity falling very slowly through the tube, so it would take longer to fall through the tube. What if holes or slots were cut into the tube? How would this affect the ring currents in your model? This would essentially create less full paths or rings that could actually induce current and create those magnetic fields. So it would decrease the magnetic field acting on the bar magnet and cause the magnet to fall faster. And a Phys tube couldn't be used because the magnet would just stick to it on the way down. It wouldn't induce any current. It would just stick to the side of the wall and it wouldn't fall through or use Faraday's law. So conclusion, just to reiterate, the time with the mu from lab 3 was 2.979 seconds, the time with the adjusted mu was 0.691 seconds, and the measured time was 0.690 seconds. So there was some error, which meant that the mu value had to be adjusted to get closer to what we observed, and this error could be from lab 3 and a slight miscalculation with that mu value carrying over into this lab, or we're not 100% sure we used the same magnet that we used for lab 3 in this lab, so that could also cause some issues.